double check, Sahil?
Yeah, I'll check once. Really takes a little bit of time. Not seeing it live yet. No, I'm not seeing it live yet. Okay, now I am. Yeah, we're good. We're good.
All right, let's get started.
Yeah.
Hello everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim.
Mikey.
This is Sahil. Welcome everybody to a brand new exciting episode of Corecast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode. We'll get to it. So without further ado, let's get to it. So Tim and Mikey, we had a previous episode on like the mathematical universe hypothesis. So for people interested in like what that's all about, deep dive into that, please check out that previous episode. And the crux of it says that like essentially the universe is not described by math but made of math. So I feel like this is a interesting interesting continuation of that formalizing the universe as a computer itself. So I guess Tim, my question to you is, if the universe is a computer, what exactly is it computing? Would my question.
Yeah, so previously, I mean, we went over kind of the perspective from different theories. Like you can approach physics from different angles, from different perspectives. For example, from Einstein's theory, from Newton's theory. And Zahir, if you were to ask this question, I don't know, like many decades ago, the answer would be different. People would have thought that, hey, the universe is computing, let's say, the energy, the movement, and the location of every particle and every constituent in the universe, right? That seems to be reasonable. And when people think of simulating the universe, that seems to be the obvious thing that it should be computing. But in the advent of quantum physics, that doesn't seem to be true anymore. And the reason is because we realize that variables like position, velocity, energy, and whatnot, these variables aren't exact. There's uncertainty on them. So certainly, if the universe is computing things, there's got to be some level of certainty, right? Because you imagine a computer as a sequential operation, one step after another. So what is it computing? So it seems like these traditional things is not a good candidate anymore. It turns out there is an answer. And the quantum physics answer is this new object called the amplitude. And it's pervasive in, I think, in fundamental physics. Every observable, everything we talk about, ultimately is linked to that amplitude. So I would say, if we look at modern physics right now, and if the universe is a computer, that the object is computing is the amplitude.
Yeah, but no one knows what that is. Wait, are you sure? Are you sure it's not computing our position? Why don't you think it's computing our position?
The thing is, in order for it to compute something, the position has to exist, right? In some sense. But the problem is, there are situations.
What we interpret as position, right?
Huh?
It's
right. Yeah.
Computing what we interpret as position.
Well, certainly, when we measure a position, you can argue that a position is being computed, but it's not always kept track of, and that's kind of the problem. Like,
yeah, well, that would be too much to ask. Keeping track of everything, that's too much stuff to keep track of in a whole universe, right?
But I would argue that if there's one thing the universe really is keeping track of, it is the amplitude.
Yeah, but that's everything. That's like
so
everything.
I think we should first set up what an amplitude is, because this discussion may go over people's heads, and then we can dive into like position and frame the context around that. So so yeah, I want to jump straight into it. So I guess, can we start off with the basics, Mikey, of like, how is the universe a computer if it is? Like, what does that even mean? Like, can you describe like a computer, how a physicist understands the computer, and translate that to like how we can think of the universe as a computer?
Yeah, like that's like a really tough question, but when I think about what a computer does, a computer is just anything that like takes a set of rules and then acts according to those rules. And I guess um, all the computers we know about, these are deterministic rules. So like you play it one way, it's going to end the same way. Aside from the whole error correction thing. Um, when I think about the universe, does like what's the job of the universe? The job of the universe is to figure out how the future is going to look like given a certain path, right? Isn't that kind of like analogous to like a video game too? Like when you're running around in a video game, like a first person shooter or something, like what is the video game engine doing? Like if I jump, the video game is it's figuring out what's going to happen next according to the rules of the game. Um, so is it? I don't know. Like just at the face of it, it would seem to me that the universe is at least doing something a little bit like that, right? Like just figuring out how the past turns into the future.
I mean, couldn't we just say that like you have the universe is in a current state described somehow in some
Yeah.
type of language, and then you have a set of like I guess rules that just evolve it forward in time or whatever you want to say
Yeah.
from one state to another state, and that transition itself is deterministic. But yeah, is that fair to say?
Yeah, I guess it depends on what you mean by deterministic, but yeah, like that's really like so. I guess one of the most fundamental experiences about the universe is that we experience like the movement of time, and that's how we have experiences. So the universe is allowing that to happen, right? It has some rules for how the future evolves from the present. Um,
I think I would say that
yeah,
what I think I would say that whatever the universe is computing, that thing has to be source of all other things.
Mhm.
If the universe is computing A and somehow we observe B and B cannot be derived from A, then that's not what the universe is computing, right? Like whatever the universe is computing has to be the fundamental source of all observations. Like whatever you see, it has to funnel into this thing that it's simulating. Like I guess in a video game, this will be like the literal zeros and ones in a computer because that can be translated into an image. It can be translated into a character moving about. But like in a simulation, there's going to be like the source code. Like it's computing the bits of zeros and ones. Like that's what a game is computing, right? But if you think of we think of the universe as something like that, there's got to be that source code, like something that everything else is derived. And I think and that's why the one candidate I think that this holds true will have to be the amplitude. I would say.
Yeah. Okay. So essentially, you can think of the universe as loosely speaking, like the state of, I mean, quantum mechanically, the state of like the quantum mechanical analogs of ones and zeros, and then there's some deterministic set of rules that translate that state of ones and zeros in quotes to a different state of ones and zeros, again in quotes. Is that a
yeah. I think
fair
the ones and zeros things
analogy?
are important, right? Um, the ones and zeros thing, I don't think that's that important, right? The important thing is that like action and dynamics occurs because of the fact that states change through time, and the amplitude is the recipe that the universe follows when it determines what it's going to do next.
Yeah, but we
So if
haven't
there was
even
such a thing as like
described.
a script in a movie, the amplitude would, I get it. Is that a fair analogy? What do you think, Tim?
Yeah, I would say kind of. Yeah, maybe. It's like the
Script in a movie,
script.
yeah. Kind of
It's
weak.
like the script, but then the actors don't necessarily have to follow them, but it's kind of what dictates what goes on. I mean, it's
It's
all a
like a
bit of
blueprint for the house. It's also weak.
Yeah. So anyway, I want to move on and just so Tim, you mentioned in the beginning things about uncertainty, and when we learn about quantum mechanics, learn that it has to do with uncertainty. Einstein said God doesn't play dice, those sorts of things. So I can't help but think like probability must come into this. So can you, before we jump into how probability plays a role in physics or doesn't play a role in physics, can you describe to the audience like how physicists think about probability? Like what is it? Like, yeah, classical
Yeah,
probability.
right. Yeah, and I think a lot of times people talk about probability very loosely. But one thing to keep in mind that is that physics really is not probabilistic. Um, and the thing to remember is, like, for example, if you take a coin flip, you flip a coin, you get heads or tails. It's not like there was really a random number generator. Like even when you look into a computer, you generate a coin flip. Like what is it doing? There is some kind of pseudo number generator. You're taking some bits of 0 and 1, scrambling it up, and the outcome kind of looks what we call probabilistic. But at the end of the day, true probabilistic events don't exist. Probability is a approximation of mathematics that simplifies our life. So if you think of it, when you flip a coin, what's really happening? There's air molecules involved. As you flick that coin, depending on the angle of your hands, any subtle differences will modify the coin flip, right? So really, to actually get the coin flip, it means that you will have to follow all the molecules in the air, which is impossible. So we use probability to approximate it. Because probability is so emergent in that way, even when we go into quantum physics, it means that it's not actually a good candidate for the things that the universe is computing, because it doesn't tell you the whole story. Like it's almost like imagining, I don't know, like imagining a TV, but in order for TV to play a movie, instead of showing you the pixels, it actually try to simulate the characters themselves. Like that's too hard. It's almost like you gotta show the more basic things in which the characters emerge. So probability is kind of like the characters. There's something deeper than that, and it turns out that in quantum physics there is one layer deeper that you have to dig deeper into.
Anything you want to add to that, Mikey, before we move on to another?
Yeah, I just think like a succinct way to say that, like, you can have a lot of time is like, you could ask the question, where did probability come from? And I think the answer would be the amplitude. Like, it's as Tim mentioned, there's like a lot of like things about probability that, like, it seems to make sense because it jives with our everyday experience. But once you start to like really think about what the implications of what it means, you start to realize that yeah, it is kind of like a artifact of our ego.
Yeah, one thing I want to point out that if I know that probability seems very intuitive to us, but it's actually really strange if you think about it. It is very.
I feel vindicated because I used to think it was like weird, and then everyone's like, "Oh no, it's like it makes sense," and I'm like, "Okay."
The problem with probability is because you lose something in a probability. Like imagine you flip a coin. Let's say the coin could be heads or tails, and you flip it, you got tails. But what happened to the heads? It's almost like the universe is losing something. Every time you roll a die, you got a 1. What happens to 2, 3, 4, 5, and 6? If you think of probability as a fundamental thing in the universe, then every microsecond, every interaction, the universe is losing something. It's losing probability.
If you're conditioned to think about probability as something that should be a conserved quantity, then yeah, it looks really weird.
Yeah, so it's very strange. And indeed, that's one of the big issue of treating probability as the fundamental thing. And that's why we shouldn't. And that's why actually amplitude makes a lot of sense if you think of it that way now.
Yeah. So before we jump into amplitude, mentioned many times, can you, Tim, I guess summarize all the different issues with, if we were to say, let's use only classical probability theory to describe all of physics, like what are the different issues that you would run into? You mentioned one, which is Like you lose these possibilities, but maybe how does that tie in with quantum mechanics? Like, why is that so bad with quantum mechanics?
Well, yeah. First of all, the fact that you lose stuff means that unitarity is lost. And previously, in many episodes back, we talked about this, the most sacred law, and it's the preservation of information, also called unitarity. It means that all the possibilities of the universe is preserved. It's never lost. Even if you flip a coin, you got heads. The information about the tails is still exists, even though maybe you cannot extract it right away. It's still there. If the laws of physics truly follow probability, then the other possibility will be gone, literally, right? Because that's how probability law is. So that's one thing. And another other problem is relativity, because we know that, in order to flip a coin, you need space and time. You need time to do the flipping.
Mhm.
And if you say that, hey, look, on Earth, when I'm flipping coin, things are random in this way, I'm singling out kind of one way of flipping coin. Because if you look at relativity, space and time are all relative. The notion of time could change and shift. So if you think of probability as kind of the sacred thing, it's actually not so easy to reconcile with the fact that space and time can melt into each other, right? And even the ordering of events, one thing happening the other, doesn't have to be sacred, Like when for example, when I flip a coin versus when I observe it, the ordering of these events it's not obvious, because the concept of space and time could modify it. And because of these problems, so basically these are the problems with probability. It messes up with some symmetries, and it also doesn't play well with the most sacred law, the unitarity.
So one question I have regarding, so I buy the quantum mechanics thing of not preserving possibilities, which violates one of the most sacred laws, or the most sacred laws we've discussed in previous episodes. But one thing regarding symmetry is like, usually when you talk about flipping a coin and you say, oh, it's like 50-50, assuming it's a fair coin, you don't mention any notion of time or like space in there. It's just kind of like, if I have this one event in which I flip a coin, it'll come out heads or tails with like 50-50 probability. So I'm wondering, like, how does that itself, that doesn't show any notion of dependence on time or space?
There's some. There's before and after, right? Before you flip and after you flip.
Yeah, but I'm just wondering, like, how would me moving in a different reference frame change that probability, or like break it? Or I'm just trying to understand the symmetry argument that you made a little
No,
bit.
I think that's why probability sucks. Like,
Okay.
that's why I hated learning it. Like, it's like you ask these questions. Like, I remember like wondering that, like, and then people are just like, oh, don't act like, like they try to make you feel stupid for asking that question. But it's true. Like, people would disagree on how many coins you've been through if they're moving fast enough.
Yeah. I mean, Mikey, let me just hone in on that point. We didn't mention time, but the fact is that the before and after, there's such a sharp distinction. Before, you didn't know. Right after, you somehow figure out the coin is heads or tails.
That doesn't make any sense.
Like, there's a jump. There's a jump in the amount of information in the universe. And this gap, and where does that jump happen? You have to kind of sit down and be like, hey, it happens in time. And you're singling out a particular reference frame in some sense, even though you didn't try to do it. But the moment you say, hey, like, there are these special points in time before and after, you screw your whole theory up. I mean, there are theories that people try that, and it's just completely a mess.
Oh yeah, if you tried to use only probability rules to write a video game engine, it would not.
I mean, it would work in a video game, but not for physics.
No, I don't think it would work.
Well, it will work in a pseudo random way, right? Like you generate pseudo random numbers.
But the underlying machinery would have to be. Yeah, I guess that's just Boolean mechanics.
All right, so I guess okay, that makes sense. So I guess now Tim, it's the question, the crux of the episode. What do we do? What do we do about this? If classical probability doesn't cut it, where do we go?
And I think that's where amplitude comes in. I mean, what the heck is the amplitude? And I think Richard Feynman has a great visualization. There are many different ways to view the amplitude. You can go very deep into the math. It's also related to the wave function, and we can, for those who are technical, you can kind of think of it as the wave function. But really, the amplitude is the summation of all that was possible and all that was in the past, and it was all added up with a weight, basically. And it creates kind of like a wave-like object. And this wave-like object can be both positive and negative, and it could be undulating in variety of different ways. And that's probably the best description of amplitude I can come up with.
I
You don't
mean,
have to get that technical, right? It's just a rule for how, like a bunch of possibilities in the past, correlate to a bunch of possibilities in the future, right?
Yeah, the key crux is that it is preserving of all the information. You sum everything up, and at no point in time do you lose anything or gain anything. All that was in the past, you sum it up, and it keeps going on in the future, one step at a time. And it also melts very well with the relativity, the symmetry of space and time. You know, you can be in a different time relative to the original, and your amplitude can shift accordingly according to the rules of relativity. There is never a sudden jump between before and after. It's just like a massive, I don't know how to put it. It's almost like it's like a voting pool. Is that a fair comparison?
Or what?
It's like an opinion, you know, like political voting. It's kind of like it's like influences. I don't, you know, it's like a vote. You know, like how do you want to influence the current state of the universe? You know, everything gets a vote, and
Way
it's
more significant than that. It's more like air.
well, everything has to vote. Like you can't just vote no. You know, like it's a mandatory vote.
all right. Do you think describing, I mean, maybe this takes us down another rabbit hole, but do you think describing it in terms of the double slit experiment could be helpful? Like this amplitude, probability amplitude, as it's called,
It's a
or
piece of it. It gets the double slit experiment because it kind of like shines a light on like one of the confusing aspects of the amplitude.
I mean,
Which
yeah, I guess I'm just trying to think of like more analogies that we can give. I don't know,
it's
Tim.
hard, right? Because the amplitude is such an abstract concept. Really, like what is it doing? Is it's like it's taking like it's assuming that like we're sitting at a point right now, and from
Mhm,
our perspective, there's a future universe and there's a past universe, and
mhm.
it's like basically the string that connects all of the past to all of the future. So it's kind of like a dictionary or like a rule book for how the universe like moves forward.
I
And it's some other, yeah.
well, okay. Could,
It's
could I
the thing
think
we should all be praying to.
could I think of it as this, like an amplitude, you know, if it's, you know, in line with, comes from quantum mechanics, so it has a notion of like all the possibilities of what the universe could ever be, will be such and such. And like
Mhm.
we're in one part of this like abstract space, and the other parts exist, but they're disconnected from us. And you have the rules of quantum mechanics that tell like how this, I don't know, how this
Mhm.
landscape sort of evolves, like how
Yeah.
we're moving through it in quotes. And yeah, and it's not really, I mean, one thing I want to ask you is it's not observable, right? You can't like go out and look at a point
Yeah.
in space and be like, okay, this is the amplitude here. Like, I
Yeah.
don't, yeah.
So I think I want to clarify that notion. There are a lot of people with a beef with this idea of amplitude, and you can also interchange it with wave function. There are a lot of people that says, oh, you know, the wave function is not observable. It sucks. That's why quantum physics fails. It's terrible. I think that's wrong. And the reason is because the amplitude encapsulates all the possibility. And because of that, it is unobservable in the sense that we cannot measure all the possibility. And every moment in time, we only see one of the possibility. So you can argue that the amplitude, sure, maybe it's not observable, but a small fraction of it is observable. Like,
But it's not that surprising. It's no different from the fact that I can't observe from any other point in space other than the point that I'm at right now.
yeah,
Right?
exactly.
Same for every other, yeah.
Yeah, so it's like the, you know, people talk about the wave function of a particle. You know, it's length. I would say amplitude is the generalization of that, basically. Like when you see a particle in a particular location with certain information, you've observed part of that amplitude. But of course, you can't reconstruct the whole thing, right? But it's true that what Micah you're saying is true. You know, like nothing in the universe we can observe it in wholesale. So that, I think that protest is a bit mute.
I see. So I guess like, I mean, so you mentioned that like this has a wave-like nature to it. I mean, what is the significance of the wave-like nature? Like, why does it need to be a wave? Why not just like some other object or something like that? Like,
Because I think that's super important because so I think we go back to the double slit experiment, right? So ignore quantum physics. Like imagine I guess the classic experiment is you shoot a gun from position 1 to position 3. And by logic, you know, something that goes from 1 to 3 has to go through 2 in let's say it's a path. So in order for you to go from 1 to 3, it has to go through 2. So you have to go through 1 to 2 to 3. Right? And if you know probability, the probability of you going from 1 to 3, you have to sum up all the possibilities, right? You have to look over how does it go from 1 to 2 and then 2 to 3. You know, and you can sum up all the possible 2s and you get 1, 2, 3. This is kind of like basic probability theory.
Additional probability.
Right. But one thing to note is that probability is always positive, you know. So going from 1 to 3, every single possibility will add up in a positive way. You will never have a negative contribution. But it turns out that doesn't work in quantum physics. Sometimes, you know, some of the physics will say like, hey, look, I don't want you to go to one of these possibilities. There needs to be something negative. There needs to be negative opinion and positive opinion combined. Like, so that's the difference, right? And this is sort of observed by observation, that probability can destroy each other. And if you just have probability theory, it can't possibly happen. So what happens in quantum physics? Quantum physics says, yes, you can, in order for you to go from 1 to 3, you have to go to 1 to 2 to 3. But we don't sum the probabilities. We sum up the amplitude, all the opinions between 1 and 2 to 3. You can add them up, and that's why at the end of the day, you can see this beautiful wave-like pattern. That's not intuitive. And
is that what you mean by vote? Like,
kind of,
like
yeah.
Probability is like the results, and the amplitude is like all the individual votes.
Yeah. I think probability, it's like you always have to cast a positive vote. Because the possibility is always 1. You can't just be like, I'm going to destroy the other possibility. But amplitude has the propensity to do that. You can actually be like, hey, look, dude, I don't like this other possibility. I'm going to mess it up. And this is quantum interference.
So amplitude is like political sabotage. Right? Whereas probability is just like a you just have one winner, one loser. Like you don't think about the fact that you can undermine. So I don't know.
So let me try to see if I got this or come up with like you know, another way of explaining this, and let me know if I'm right. So from what I understand from the double slit experiment, you have like a gun that shoots out electrons. You have a screen like at 0.3 as you're mentioning, and then you have a barrier in the middle, which is 2, which has 2 slits that are going through it. And you shoot a beam of electrons, and they either go through slit 1 or slit 2 at position 2, and they hit the end of the screen. And if you keep the quantum mechanical nature of the electrons intact, meaning you don't shine a light at either one of the holes, what you end up seeing on the third screen is like this wave-like kind of thing where you see places where it's like hit and then like dark spots. So imagine if it were light itself, it'd be like bright spots, then dark spots, bright spots, and dark spots. So can you think of the probability itself, or this amplitude rather, as describing like the position of where I would expect the electrons to be? And because there are certain dark spots in that pattern, that would indicate some cancellation, which is the negative part of the amplitude coming in. Is that a fair assessment?
Yeah, I think that's a fair assessment. Although for the general audience, this might be a little bit convoluted. I mean, it really is. It's just a statement that probability, you don't just add. You don't just add probability. You can add and subtract. And actually, I know the double slit experiment might be a little convoluted, but you can try this with sunglasses. It's essentially the same thing. The concept, like if you take if you have a sunglass that's polarized, it blocks light. You can say it blocks light 50% of the time, right? So if you have a polarized sunglass, you look at light, you see that, oh, the light is darker. If you have two pairs of sunglasses, one block the sun from one way, the other block from the other way, 50-50, you see that there's no light. You block 100%. You add them up, right? So using classical physics, if you add more sunglasses, you're gonna block more light. There's no other way around it, Like if you add more sunglasses, how is the light gonna come through any easier? You have more barriers, right? Quantum physics says that, hey, look, if you actually put a sunglasses in the middle and you dial it, you rotate its orientation, you actually see more light coming through by adding more barriers. But in some sense, this barrier is like a negative barrier, because as opposed to just subtracting probability in this case, because it's a barrier, the opinion of, hey, where the light should be kind of goes up and down. It's not obvious anymore. It's more complicated. There's like a vote going on, kind of. You can think of it that way, right? Every particle is in this, all the histories of the entire of everything is culminating in this experiment. And once you sum it up, a probability emerges. Then that's how you can explain that. Hey, look, if you add more sunglasses, actually more light goes through, which is not intuitive.
I see. Yeah, that makes sense. So classically, if I were to add in more sunglasses, I would expect the light signal to get more attenuated because there are more barriers. But quantum mechanically, if I happen to arrange these barriers in specific orientations relative to each other, I can end up seeing more light coming through. Is that correct?
Yeah, I think that's absolutely correct. It's just that quantum physics just tells you there's a more nuanced world,
Gotcha. Yeah, so actually now we've set up Amplitude as, as best as we can. And now beginning of the episode, we talked about the universe is computing this object that we call the amplitude. So how is it doing that? Like, how can we link these two things together? Like, yeah, how does the universe and amplitude work together in terms of this computational type of like I guess like paradigm or description?
We have no idea about that, right? Like if so, right? Like if someone's like, if we just like imagine like a really dumb version of a universe, that's written by like some software engineer who's just like designing a game and we're all living in it, right? Like I don't know if he chose to write the program in C# or like Python or like whatever. Like yeah, we really have no idea. But like one of the things that's interesting is it doesn't really matter. It doesn't matter what the, I don't know, if there's a designer, it doesn't matter what language they're using to write the program. The amplitude, like it doesn't matter what programming language you use to write like Warzone or Halo or Super Mario Brothers, but it's using the same, same physics engine with the same rules.
Well, one question about that analogy, like different programming languages have different operation speeds. Like if I write something in Python versus like C++ or even like assembly, there's going to be a distinction of how fast it runs. So
yeah,
how does now just want to see if that's what
we can detect that though, right? Because like for us, the clock speed is like like actual time. So we can't detect like any kind of lags, but
Mhm.
um, hmm, I don't know. Yeah, we wouldn't be able to tell, right?
I mean,
Um,
I would say there are different parts of the amplitude, right? Because I mean, you can look at the amplitude of us chit chatting. Ultimately, that comes from an amplitude. But if you zoom in, probably that amplitude itself is coming from the amplitude of more fundamental bits. Like the protons in my hands and the electrons in my hands are doing something to give the appearance that I'm chit chatting. So at least we know that the um, basic particle physics roughly tells us how the rules of large the particles we know behave. So in some sense, we kind of have the big picture, almost like a zoomed out pixel view. You know, like you zoom out, you see these characters emerging from the pixels. You roughly see how the amplitude behave. But if you zoom in, you don't necessarily know the details. But that's okay. The nice thing about the amplitude that it is actually is built up piece by piece. It's able to do that. You can build it up by one time slice after another, or one small location after another, and it's kind of like a big puzzle. You know, like all the history kind of culminate in one part or another part, and you kind of just build it up, and you build this massive amplitude.
like Lego block.
And I think that's a fair analogy. Yeah.
Actually, now, Tim, I want to ask you. You mentioned before that classical probability, doesn't work with the symmetries. How do you explain that with amplitude? If like this notion of like time, like marching forward. So, just want to ask about that. Does it preserve
Yeah.
symmetry?
Yeah, the reason why it preserves symmetry is because the amplitude is able to change. Because the amplitude is not absolute either. It also depends on space and time. So if you have um, a change in your reference time, the amplitude can adjust accordingly. But it's much harder to do that for probability. Like people have tried. Like you can write down a theory with just probability, but then this sharp divide between before and after just kind of screws you up. What ends up happening is that people still need to introduce a new object, like a guide or whatever, that kind of behaves like the amplitude. And at the end of the day, it defeats the whole purpose. It's almost like if you try to get rid of the amplitude, it comes back to you, basically. So let's just say the amplitude is there. Something like it is there.
Hmm. And then, Tim, have there been any attempts in physics? Maybe we could spend maybe like 1 minute or so describing this, but have there been any attempts in physics to like use only classical probability theory, like no amplitude business, just that's the only thing kind of a thing.
Yeah, of course people have tried to do that because everyone thinks that like, oh, the way I experience things must be the way it actually is. So we like, yeah, we'll spend a lot of time trying to prove that.
Yeah, but it doesn't work, right? Like I think these go under the name of Bohmian mechanics. I mean, I don't want to throw shade in some people doing research, but this is almost like back in the days. They just feel like they couldn't accept this new way of viewing the world, quantum physics, and they just kind of held on to the old view. Be like, oh, a particle has to have a position, has to have a momentum. But we've already know that particles doesn't need to have a position. The position only shows up when you measure it in some sense. Like you interact with the amplitude that has information about the position. That's the best way to put it, right? You get a position when you poke the amplitude, the part of the amplitude that has position information. Then you get you get the position. But I mean, the thing is, when you insist on doing that, when you say, "Hey, look, particles gotta have position, momentum," they couldn't accommodate modern physics, basically. They couldn't accommodate the fact that particles can pop in and out of existence. Positions and energy momentum could get created out of thin air when particles get created and they disappear. And the whole theory it looks crazy. Like then they end up having these really strange objects that kind of like have to follow the position of every particle. It's just weird. Might as well just not have it. So
Fair
Yeah, they're
enough.
annoying.
Yeah. I guess Mike here, Tim, wanted to ask you, like you mentioned things about quantum fluctuations of particles appearing, popping in and out of existence and then disappearing. How how does that work with an amplitude? Like, how does that work with possibilities? Like, how do I just think about that? 'Cause it seems like it's a new possibility for a particle to appear and then disappear. Like, is it, just how does, what does that mean amplitude wise?
I think Mikey, I think all of these discussions in the past, it would have been more accurate to frame it in the amplitude way. I think, like particles can
Instead of
come.
probability.
Yeah, I think so. I think probability just make it kind of easier to relate to, but really at the end of the day, particle
Does it
pop
make
in
it
and
easier to
out.
relate to? Hmm. Hmm. I don't know. What was
Yeah,
the question
but
again?
The question is like, now we've framed thinking of the universe in terms of the structure that we call the amplitude.
Yeah.
How do you explain particles popping in and out of existence with this amplitude framework? Like,
Oh,
what
the
does that?
amplitude tells you. The amplitude tells you like how many particles you're likely to see.
Hmm,
And if I happen to be moving really fast with respect to you, you're going to see 3 and I'm going to see like 10. And
hmm.
the amplitude carries all that information, like the difference between what you're going to see and what I'm going to see. And probability does not carry that information. And I think that's really what makes the amplitude work as the generator of probability. It
Gotcha,
has to be
gotcha.
something that generates probabilities because probabilities cannot, yeah, explain that you and I see something different when we look at the same thing.
Fair, fair. So we have a few audience questions that I want to get to. One of them is audience members asking what Roger Penrose's perspective on this would be, is i.e. QM is inconsistent or quantum mechanics is inconsistent. Because I don't know if you guys know what that question's referring to,
He
or
probably likes Bohmian mechanics.
that's the
yeah, I'm not sure about that. I know Roger Penrose is more of a mathematician. I
And quantum
mean,
mechanics make them uncomfortable.
yeah, I mean the thing about physics is that like sure, physics is not is not 100% mathematically rigorous.
Yeah,
But
and how are we
like
going to make people comfortable all the time with these crazy concepts?
yeah, but like it is what it is, you know, like our brain doesn't have direct access to the quantum mechanical realm, and I'm not surprised that it's hard for us to think about these things. Maybe we'll never be able to fully comprehend these concepts, you know, except on an abstract level. But I think we should be okay with that. Like our
Yeah.
brain is a very particular object. Why be constrained by our comfort and use that to dictate our physical theory? I think that's short-sighted.
If you think that the universe is weird, it means that you're weird. That's just about a rule.
I'm gonna use that on people if they've sorry. So then we have another audience question, which is do the atomic vibrations sorry, is atomic vibrations a source of true randomness or random numbers?
I would
By
say
atomic vibration, you mean quantum fluctuations of atoms? Then yeah.
yeah. I would say, well, first of all, what is true random? I think that concept doesn't necessarily exist, but the closest thing you can get is, yeah, if you grab some quantum mechanical system, that's probably the best pseudo random number generator you're ever going to get.
Why pseudo?
Because nothing is truly random, I would say. Because the definition of
Exactly 50% between the axes, or
well,
when you measure it?
it just irreducibly impossible to predict, right? Like a pseudo random number generator, you can predict roughly if you know the seed.
Mhm.
Like the atomic, if you grab a quantum mechanical system, there is no seed in which you can predict the outcome.
Yeah, but Stern-Gerlach is pretty close to pure random.
Right. I think true random in terms of the human way of thinking about it, but there is nothing that's truly random because think about
Or from quantum mechanics.
yeah, like even quantum mechanics is not truly random in quote unquote in that way because like in probability theory, what is random? Random means that you have to repeat something 1,000, 1,000,000,000,000 times, infinitely many times, and you get like a distributional answer. But literally in the rules of quantum physics, like remember, quantum physics tells you that it preserves all the information. Probability does not. So one of the
you can always single out a subset of trajectories.
but it's not exact, right?
Random.
I mean, quantum physics tells you that you cannot, you literally cannot repeat anything, hands down. Like you cannot repeat any experiment exactly, hands down. So just,
Mhm.
and part of that is because of this peculiar theorem, or this requirement that quantum physics preserves history, preserves possibilities. So you can never repeat an experiment perfectly. So
Well, of
then
course, I mean, the state is never going to be exactly the same as it was before. The state of the universe.
yeah, and yeah, exactly. So I guess to answer the
But I
question,
can still make a little box around this part.
I think you can get true randomness close to what humans think of as true randomness, but like
You can
not.
asymptotically approach it by isolating yourself enough from the universe, right?
Fair enough. I mean, yeah, that I would agree with that. That there's no true randomness. Based on the reason you gave, Tim. So okay, so then last question for me, before we wrap up, is so as we've discussed in past episodes, we've alluded that quantum mechanics itself is approximate in describing nature. Like every theory we have is effective. There's no true fundamental theory. So I guess like does that mean that this amplitude is like not truly fundamental, or like is just an artifact of like quantum mechanics is the best theory we have to describe things in the regime that it's valid for, and so happens that we model everything after an amplitude? Like you can't really measure it, so you don't really know it exists other than that the outcome of using it seems to match up with experiments. So thoughts on that from both of you?
Hmm. This seems like there's something special about the amplitude, though. Like something worth praying to. I don't know.
I, I would say that it's plausible. I mean, I don't think I'm 100% subscribed to amplitude being the ultimate truth, whatever that means, right?
Yeah.
Like I think sure in the future we could have a better theory and where amplitude will emerge from something else.
No, but
You
it's
know,
going to have to be shown to be pretty closely equivalent in structure to whatever
right?
replaces it.
Yeah, I would say, once again, we can call back to our episode on the space of theories. I would say, in the level of approximation that we have in the real world, amplitude is the closest thing. I mean, chances are in the future we might have some other theory that subsumes the current understanding of physics. It doesn't mean that the idea of amplitude just go to the trash. It means that, hey, amplitude is approximate. There might be something else that comes along, and for example, Nima has been doing some work on what we call amplitude-hedron. Maybe that will be the root of amplitude. I don't know, right? That's a possibility.
Certainly shows there's a lot more to the amplitude than we previously thought, which is almost hard to believe, but
I see. So, Mikey, you seem convinced up to the point of like religious conviction in the amplitude, and Tim, as usual, seems skeptical.
well, I'm just saying, like, I think it's different. Like, so when Newton discovered his laws of motion,
Hmm.
you could have like, and like if you were I don't know, yeah, I don't know, like a little like as unsophisticated as 17th century scientists were, like you could think that, oh, that's like the amplitude, like what he found. It's like it just does it gets everything perfect, got the sun's planetary motion, everything. It's like Newton's rules are like the key. And I think like at that time you would have been right. That's like pretty much as close you would have come, but I don't know.
But Newton was uncomfortable. He was uncomfortable with the fact. Well, in Newton's world, he thought about forces, push and pull, and he thought that was kind of the sacred, kind of the Bible or whatever, the truth of the universe. But he was uncomfortable with the fact that the sun is able to exert a force so far away instantaneously. Right? He was uncomfortable with that. And he was right. Indeed, that is not the truth. The truth is actually Einstein's idea of the fields, the metric field, the space-time field, so that the force is actually generated from a field that can propagate from the sun to Einstein.
And
I would
certainly you can make the argument that we could be in the same position right now, like talking about like, oh, the amplitude is like, like the sacred thing that determines how the universe moves. But don't think it's exactly the same as that. I think we're pretty close. I don't know, just doesn't it feel like we're kind of close now to like touching the fundamental truth? Like when it's this simple, when like all you have to posit is like just one geometry, and it gives you like every single transition in the universe that happens in every reality. I don't know.
I guess Mikey. Oh, go ahead. Sorry.
Oh no. I you know. I just feel like it's an accomplishment, like the discovery of the amplitude object and our ability to transform society through this realization of the massive simplification of laws of physics that have come about it. I don't know. I just don't think we should like throw it in the like people have thought this before. We probably still don't know anything right now. I don't know. I feel like it's tempting to say that. I know for people, but might not be true.
Yeah, understandable. Okay, so one follow-up I want to mention is that you mentioned in many previous episodes, Mikey, that if you can't measure it, does it exist? And so I ask you the same question with an amplitude. Can't measure it, does it actually exist?
It doesn't matter. You can still pray to it. It's presence of stuff.
I appreciate that answer. So we're almost at time, so I want to give you guys a chance, and in our tradition of like leaving the audience with any words of wisdom that the amplitude has bestowed upon you.
Yeah, I would say, when you first learn about the amplitude in quantum physics, it seems very strange. It's like, hey, you have to sum up everything. It's almost like, it almost feels very inconvenient. Why do you have to go through this?
Does it kind of sound like the truth, though? I'm sorry, I didn't interrupt.
Well, I mean, in the beginning, when you first learn it, it kind of feels very strange because you're not used to it. Yeah.
You didn't feel strange when you first learned it. I remember when you first learned it. We were like, "Whoa, this is like awesome.
No,
This has to be true."
but I think when you first learn it, you don't really understand what it is yet. But I think over time you start to appreciate it, and it actually gives you a little bit of comfort because it tells you that there's almost like a little bit of kindness from the universe.
Everything matters.
It's almost, it has a little bit of vibe of democracy in it. Like everything in the universe adds up. Like even though we live in an uncertain world and we don't see all the possibility, it's like oh, instead of going on a walk today, I played tennis. What if I'd done the other thing? That possibility is not lost in the universe. Maybe it will show up somewhere else as noise, but it's out there, right? And at the end, and it also gives you this sense of, it almost feels like it's one of the closest thing to a religious experience. I mean, I hate to bring up this word. Like, we are part of the amplitude. Guess what? If there's an omni-powerful computer calculating how the universe is going to go, we're part of it. Like right now, we're literally part of the amplitude. You can draw a Feynman diagram with Sahil, Tim, and Mikey popping out and having a chit chat. It's in the computation. So in that way, I think I would feel a little bit of comfort.
Yeah, for sure.
And I think that's my wrap up for the day.
Oh, we gotta continue this. I don't know. Yeah, it's just too hard to wrap this up with something super poetic, but yeah.
Are those your final words, Mike?
Oh, no, I scrapped the final words. So yeah, just run it back for next week.
Okay. All right, so we'll leave it at that. So actually, sorry, last audience question coming in, and then true wrap up. So if it did not repeat, won't this be truly random? Following that atomic vibrations is a true source of randomness question.
Right. Yeah. Let me just follow up on that. So it means that the definition of randomness is screwed up, because if you look at a statistics textbook, for a random number, to define a random number operationally, you need to repeat an experiment x number of times, and then you take x to infinity. And in quantum physics, you can't even repeat it once. I mean, you can approximately repeat it in real life, Yeah, but that approximation has a limit. So yes, then it means that it's not truly random in that way.
Gotcha. All right then. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
See you all.
Wow.
Bye bye.
Bye.